In this chapter, we are looking at sequences and series. In this lesson, we're going to focus on geometric series.
So a geometric series is really exactly what you would expect it based on what we just looked at in terms of arithmetic sequences and series. So a geometric sequence, okay, is just this sequence of terms, okay, that where I multiply, okay, by a constant to go from one term to the next. In a series, I'm just going to add them all up. Okay, so now we're going to build the formula. There is a formula for adding up the terms in a geometric series, and we're going to develop it in a similar way to what we saw little Gauss do with arithmetic series. Okay, so let's take a quick look here. We're going to take, and we're going to add up, actually I'm going to zoom in on this a little bit here. We're going to add up the terms in a geometric sequence. Now, and that's going to look like this. We're going to start with A, and then we're going to have AR, and then we're going to have AR squared. Okay, and then we're going to add these out, dot, 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 and then we're going to get, okay, our last one out here is going to be AR to the n minus 1. So the one just before that would be AR, let's say, to the n minus 2, and then out here AR to the n minus 1. Okay, because every time I add one, that number is going to go up here. Okay, so now what we're going to do here is I'm going to put another one underneath here. Okay, but I got to be a little bit clever. It's not exactly like arithmetic sequences. If I just did this underneath it here, it got all the exact same things. Even if I switch the order, it wouldn't do much here. But watch what happens when I do this. I'm going to multiply the sum here by r. Okay, now I didn't come up with this. I wish I could claim that I was as clever as that to do this here, but I didn't. But if we multiply that sum there through by r, then what we get here is AR plus AR squared plus AR cubed, okay, plus dot, dot, dot. Now, if you multiply this one by r, I'd have to add an r to this. I'd have to add 1 to the exponent, which would convert this to AR to the n minus 1. And it would convert this to AR to the n. Okay, because I would just add 1. What I'm doing is I'm just adding 1 to the exponent of r all the way across here. Now, just take a quick look. Zoom out here a little bit. Take a quick look and compare these two sequences. Or these two series, I should say. Notice, okay, those are the same. Those are the same. And we can hypothesize that these are the same all the way across here. And these two are the same. There's a lot that's being shared between these two. So now what I'm going to do is I'm actually going to subtract. I'm going to subtract this bottom sequence from the top one. Now, on the left-hand side, I'm going to get the nth sum minus r times the nth sum. But the real magic is what happens on the right-hand side. This term right here doesn't have any kind of counterpart down here. So a minus essentially nothing is just going to be a. But AR minus AR disappears. AR squared minus AR squared, okay, the AR cubed is going to cancel, the AR to the n minus 1, the square, AR to the n minus 2 will cancel, AR to the n minus 1 will cancel with this one right here, and I'm going to be left with this one. It'd be like 0 minus this, so minus AR to the n. Well, that is a spectacular simplification, okay? So now all I really want to do is simplify this. I want to get Sn by itself, so I'm going to factor that out. Okay, so let's kind of zoom in on really what's going on here now. I'm going to factor out the Sn from these two terms. Now remember, this is not S times n, it's S subscript n. And I'll be left with 1 minus r. I'm also going to factor out the a here, so this will be a times 1 minus r to the n. And now to get the Sn term, the nth sum by itself, I will divide by 1 minus r. So Sn is equal to a 1 minus r to the n over 1 minus r. And look at that. What a wonderful little compact formula for the sum of a geometric series. Now, we should tell you right now, you're not often going to see it written like this, though. It's just kind of formality, the regular way we do things here. When you've got 1 minus something else, we like to actually have this the other way around. It looks better to write this as r minus 1. So what I'm going to do is I'm going to change the order of these things. And I do that by factoring a negative out of the top term and a negative out of the bottom term here. So that will look like this. We'll come up here. Okay, I will take a negative 1 out of that, and that'll change that to r to the n minus 1. Take a negative 1 out of the denominator, be r minus 1. And so now the negatives will cancel. I'll be left with a times r to the n minus 1 over r minus 1. And that is typically the way we will write that. And in fact, down here, here's that formula right there. Now there was a little bit of an issue there. If you zoom in on that note there, you'll see that I accidentally put the wrong parenthesis there. But so put that right like that, and ar to the n minus 1 over r minus 1. Now there is another way of writing this, okay, where we write r times the nth term minus a over r minus 1, and all that really is just a reworking of this particular equation right here. If you multiply that a through, okay, ar to the n minus a over r minus 1, just, whoops, sorry, you can't even see that. See this term right here? ar to the n, ar to the n. Where have we seen that before? Well, that was up here. Whoops, sorry, that was right here, ar to the n. And I got this term by multiplying my last term by r. Okay? So I get ar to the n by multiplying, and there it is right here, the last term by r. Anyway, so here are the two formulas that we're going to use for the summation of the first n terms of a geometric series. Okay, now, for the rest of this lesson here, we're just going to look through a set of examples, and it really is just going to be about utilizing these formulas, kind of manipulating the equations to find a variable given other information.
Find the sum of the first 7 terms of the sequence -3, 6, -12, and so on.
So in this example right here, we're going to look for the 7th sum. Now that means that our n variable here in this particular problem is going to be 7, because remember the subscript of the s there should be the n variable. Now let's take a quick look at our sequence here. The a value here is -3, and our r value, now notice it's an alternating sequence here, so our r value is going to be negative, and to go from 3 to 6 we're going to multiply by -2. So now to find the 7th sum, we just got to plug these things into our equation here. And I'm just going to use the first one that we had up here, ar to the n minus 1 over r minus 1. It's actually pretty simple to set this one up here. It'll just be -3, there's my a, times -2 to the 7, and you want to make sure that you put brackets around that so that you include the negative in that, okay, because that's important. Minus 1 all over -2 minus 1. Okay, now this just becomes calculator work at this point. You just got to make sure that you've entered this correctly here. Don't make the classic mistake here of not putting parentheses around the entire numerator and the entire denominator. Okay, often I'll have students tell me, no, I know I've done this all right, everything's correct here, but I'm getting a different answer. And really, almost every time that happens here, it's because they haven't put brackets around the numerator, brackets around the denominator. The calculator doesn't know what the numerator is, it doesn't know what the denominator is, so you have to tell it. And when you do that, you should be getting -129. Okay, that's the sum of the first 7 terms of that series.
Find the sum of the series 4 minus 12 plus 36 out to -8,748.
Now I like this question here because I like to contrast it with what we would have done in the arithmetic series section here. If you had a question similar to this in the arithmetic series, that question would have actually been very difficult. But in this case right here with a geometric series here, it's actually not that bad here. Notice that the first term here is 4, okay, and that my r, now notice again it's an alternating sequence, and so my r is going to be negative, it's going to be -3. But I know the last term. I know what we call the nth term here. I know that that last term is -8,748. Now, because I know the last term, I'm very tempted to go up here and use this one right here. Now, take a good look at this equation here and notice something a little different about this one when you compare it to the arithmetic series equation here. This one does not depend on n. I don't need to figure out how many terms there are in the sequence to figure out the sum. And actually, that's kind of neat. So when I come back to here, I've actually got all the information I need. So I still don't know how many terms there are, but I know that I'm going to multiply my r by the last term. So negative 3 times negative 8,748 minus 4. Whoops, I should put brackets around that. Minus 4. And this is all going to be over negative 3 minus 1. Okay, there is no unknown in that. And so now I'm going to go to my calculator. Okay, and I'm going to, got a lot of reflection there. So what we'll do here is I'll enter this in. So brackets around the numerator, brackets around negative 3, and then this will be negative 8,748. Okay, so I put brackets around those numbers, and the calculator knows that that means multiplication, and I'll subtract 4. Close brackets for the numerator, divided by, I'm going to open bracket, negative 3 minus 1, and then close brackets for the denominator. And the answer is negative 6,560. Okay, so negative 6,560. There you go. Neat question, because you don't need to know how many terms there are in that sequence.
Determine the sum of the series 1/16 plus 1/4 plus 1 out to 4,096.
Okay, this question right here is very similar to the one that we just did. Okay, again, I can tell what the first term is. I can see it right there, 1/16, and it doesn't take me long to figure out what r is, but you got to be careful with fractions here, okay? Remember that it's going to be 1/4 divided by 1/16. Now, if you're not really a big fan of that, just think about, take and compare these two terms here. What's 1 divided by 1/4? Okay, well, the answer is going to be 4. Okay, and just think about, what would I have to multiply by 1/4 to get 1? Well, I'd have to multiply the numerator by 4. So that's actually pretty easy to figure out there. I know that the last term is 4,096. So again, I can use that second formula there for the geometric series here, the sum. And I don't need to know how many terms there are in this series here to get the answer. So r times 4,096. Oh, sorry. No, that's right. Minus a, which is 1/16, all over 4 minus 1. And then this just becomes, once again, calculator work. Sorry, I got a little bit of a cold here. So bracket for the numerator. So then 4 times 4,096 minus 1 divided by 16, close bracket for the numerator, divided by open bracket for the denominator, 4 minus 1. Now, I probably could have just written 3 there, but anyway. Press enter. Okay, so now we're getting this decimal here. Now, the reason for the decimal is because of this 1/16 here. So, but we can go to the calculator, and if I press my math button right here, okay, math, my very first option that I get here is convert to fractions. So press enter to choose it, and press enter again, and then I get this kind of an ugly number. However, it still worked out to be a fraction. So 87,381 over 16. And that's the answer that we're looking for.
How many terms are there in the finite series 2 plus 4 plus 8 plus 16 and so on if its sum is 4,094?
Okay, well, to answer this question here, what we got to do is look at the two formulas that we've got. Okay, and I'm looking for the number of terms in the sequence, so I'm looking for n. But notice that this equation right here isn't actually a function of n. Now, granted, you see an n in it, but those are subscripts. They're not actually in the calculation. They're just part of the names of those variables. But over here, in this one, we do have the n. The n shows up as the exponent on r, so that's the one that we want to use here. So let's just identify the pieces that we've got here. So in this case, this is the sum is going to be 4,094. Okay, we know that the a value here is 2. And I mean, we can see quite quickly that the r value is also 2. I'm multiplying by 2 to get to the next step there in every case. So 4,094 is equal to 2 times 2 to the n. I don't know what that is yet. That's what I'm looking for. Minus 1 over 2 minus 1. Now, what I love about this is I'm dividing by 2 minus 1. Well, 2 minus 1 is just 1. So that's really not doing anything here. Whoa, that was a weird way to write that. So 4,094 is going to equal 2 times 2 to the n minus 1. Now, I'm just working my way towards that power there. Okay, I got to get towards this, so I got to slowly get rid of the other pieces here. So 4,094 divided by 2 is going to be 2,047. And that'll be 2 to the n minus 1. I will add 1 to both sides. Okay, now, if this is going to have a solution, this has to be a power of 2. Okay, and so this will take a little bit of time for you to play with here. In math, the next level of math, when you take logarithms, you'll see there's another way of solving this. But for right now, you're just going to have to play with this and find what power of 2 this is. Now, it turns out this is 2 to the 11. Okay, so if 2 to the 11 is equal to 2 to the n, we know it must be the case that n is equal to 11. So there are 11 terms in that particular series.
Remember the clever child who convinced his mother to only give him a penny for his allowance, but she was supposed to double it each week? If he saved all his allowance, how much would he have in 20 weeks?
So in this question here, the assumption is that the child is not spending the money. Okay? So for the first, in this case, it's 20 weeks, just 20 weeks. For the first 20 weeks here, nothing's being spent. So, you know, that penny comes in, they keep it. Next week, the 2 pennies come in, they keep it. Question is, how much would there be accumulated after 20 weeks? So now this is a summation. Okay, and so we know, first of all, that n is going to be 20. Okay, because we're going to sum this up for 20 weeks. Additionally, we know, based on the scenario here, that we're starting at 1 penny, so 0.01. And our R value is 2 because we're doubling. Every week we're multiplying the value by 2. So now we don't know what the last term is, so we're going to use that first equation there. So the sum of the first 20 terms is going to be 0.01 times 2 to the 20 minus 1 all over 2 minus 1. Okay. Now, this is really just calculator work. And what I like about this one right here is that the denominator is 2 minus 1. So 2 minus 1 is just 1. So that's really not doing anything to the calculation. So you can kind of just ignore it and just focus on the numerator. And when you plug that in your calculator, you get that after 20 weeks, you'll have, or this child here will have accumulated $10,485.75. Hey, that's a pretty good income there from just doing some chores.
Remember the bouncing ball? Dropped from 70 meters that only bounced up 80% of the previous height? How much vertical distance did the ball travel through when it hit the ground for the 6th time?
So we're coming back to the ball. Okay. Now, in this particular case here, we're asking for the total vertical distance that the ball traveled. So you have to think about it this way. If I was to stand here and throw a ball up in the air, and I throw the ball up 3 meters, and it came back down 3 meters, how far did it travel? Well, it traveled 6 meters. 3 meters up, 3 meters down. That is the idea that we need to carry into this particular problem here. So let's just kind of model this out here. Starts at 70, hits the ground, bounces up. So here's our ground here. First bounce, second bounce, third bounce, fourth bounce, fifth bounce, sixth bounce. So this is where we're stopping. Okay, 1, 2, 3, 4, 5, 6. Here's our 6th bounce here. Now, it's pretty clear, or at least I think most people would say it's clear, that the first term here is going to be 70. A is going to be 70. Now, the question is, how many terms are there? Now, this can get a little bit confusing because in the previous iteration of this question, when we did it, I asked you what was the height, for example, after the 7th bounce, but I said after the 7th bounce. And that introduced a new term after that bounce here. Now, in this case, if I just count up the heights here that I'm adding, it's this height right here, then this one, this one, this one, this one. That's term 1, 2, 3, 4, 5, 6. I've actually only got 6 terms here. Okay. And now the last little bit that I need here is my r. I need to know what I'm multiplying by, and in this case, I'm multiplying by 0.8. Okay, so the sum then, because we're going to total these up, the sum of these 6 terms will be 70 times 0.8 to the 6, okay, minus 1, all over 0.8 minus 1. So now that just becomes calculator work. So we'll go to the calculator here, just push that off to the side a little bit so we can still see it. So the calculator here, we got 70 times 0.8 to the 6 minus 1, close the brackets, divided by open brackets, 0.8, oops, sorry, 0.8 minus 1. And we're getting 258.25, let's say, we'll just round that, okay, equals 258.25, approximately, because I rounded that a little bit. Okay, now I'm going to leave that number in the calculator because it turns out this number is incorrect. Okay, the total distance that the ball travels is not 258.25. What that is that's the distance down, 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 down. At no point here do I include the distance up. So if I want to figure out the total that it travels, I need to take and multiply that sum by 2. Okay, so if I take and multiply that sum there by 2, whoops, sorry, you can't see that. Multiply by 2, I get 516.499. Okay, so 516.50, let's say. So 516.50. Great. That's not the correct answer. Okay, now let's think about this. I think the doubling sort of makes sense here. Okay, I'm doubling them because the ball goes up, ball goes down, so it's doubling every one of those terms there. But take a quick look at this. Doubled, 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 doubled. Ooh, this one isn't. That first term was never doubled. Okay, we started from the top and dropped it down. Okay, we didn't start here and throw it up. It started up here and came down. So this term here should not have been doubled. So to make this correct here, I actually have to subtract 70 from that value, and that gets me 446.5, and that's the number that we're looking. Now these are all kind of approximate here because I'm rounding, but that's what we want to do here. So if we choose that dropping height there to be the first term, that affects how we count off our terms, and we got to be consistent with that. Now if you chose it to be the height after the first bounce, that's a little bit different. Okay, the number of terms is different, and then you would end up having to add 70 to the answer here. But that's not how I think most people will do it. Most of us are going to start here, say this is A, okay, think about how that affects your term numbers, and then realize that each one of these heights is going to be doubled except the first one. And so I have to subtract that first height off at the end there to get the correct answer. There you go.